the place where we left them yesterday. So we were trying to prove this statement. Okay, we are going to use it mainly for gamma equals 2, but I wanted to prove it for more values of gamma, just because this thing really tells you something about well, the asymptotics of xn. And yeah, before doing the remaining task, which is proving this for gamma between 1 and 2, I just wanted to show you a consequence of this thing here for gamma smaller than 1. Okay, and the statement was the following. Let me call it an intermission. If E rho 0 gamma is smaller than 1, okay, and if xn star denotes the current maximum of the walk at time n, we have that the limit of xn star over n gamma when n goes to infinity is equal to plus infinity. Okay, so this information gives you a lower bound on the rate of divergence of xn. Okay, it gives you a lower bound only on xn star, but actually, like xn will kind of always be close to xn star in this setup. It can go back, but not by much. At most by log n, I think. Okay, so yes, this is an observation. So we have that. Okay, I don't know if I will prove it in the class, but this thing is finite almost surely. So if you have this for xn star, you have this for xn. Okay, so this is one thing. Okay, and this is when okay, this is true. Okay, this is the assumption that you have everywhere here, that we are transient to the right. And the limit of xn star. Okay, and the second observation, again, I don't know exactly what we are going to prove in the end, but what is true is that if rho 0 to the gamma is equal to 1, and gamma larger than 0, then this thing converges to a non-trivial random variable. Okay, gamma in 0, 1. Okay, so this thing is, okay, it's not exactly sharp, okay? Here I have limit, okay, limit. It's not exactly sharp, but it's kind of close to B sharp. Okay, so if you take here equal to 1, basically, what will happen to lim sup and lim inf? Okay, so this is convergence in distribution. Okay, and what happened to the exactly for this value of gamma, the lim inf will be equal to 0, the lim sup will be equal to infinity. I mean, just like what happens for Brownian motion, you know. Okay, and if you want to have a non-trivial lim sup and lim inf, basically what you need to put some logs, and this is the equivalent of law of iterated logarithm. Okay, so this is what holds. We are going to prove something much weaker. Okay, so the result here only gives lim xn over n to the gamma minus epsilon equal to infinity. Okay, if this is true, basically, well, this thing will be smaller than 1 for a gamma slightly smaller, okay, just by convexity. So this is what you will get. Okay, so what's the proof of this? Well, it's actually very simple. So the proof is simply the law of large numbers. So it starts with an observation. We only need to show that the limit when xn star over n is positive almost surely. Okay, why is that so? Because if E rho to the gamma is smaller than 1, then E rho 0 gamma plus delta is smaller than 1 for some delta positive, just by continuity. Okay, and you know, when you're using continuity here, you're using uniform ellipticity, for instance, because this thing could a priori just jump to infinity after gamma, after this value. So basically, continuity is obtained from dominated convergence, and for the dominated convergence, you need some domination hypothesis. So uniform ellipticity is. And then this thing implies that lim inf xn over n to the gamma plus delta is positive, which implies, okay, that if you take away the delta, you get infinity. Okay. Let me call it star. This is star. And of course, we are going to prove things about tau k rather than xn. So this thing, I think it's equivalent to okay, so I have to be, yeah, so it's equivalent to lim sup of tau k to the gamma over k. Ah, yes, okay, no, this is easier. This is equivalent to liminf to k over tau k to the gamma positive. Okay, why is it so? Well, it's simply because, well, this thing, it's clearly minimized at times tau k. Okay, because at time out of tau k, basically, well, they are larger than, well, basically, n is always, yeah, but you have that. N is always larger than tau of x star n. Okay, so you can replace this by tau of x star n. Okay, and then we are done, because okay, what we will have to apply is only the law of large number. Okay, so we are using the ergodic theorem. So why are we using the ergodic theorem? Well, tau k. Okay, let's say that ui is equal to tau I minus tau I minus 1. Tau k to the gamma. Well, gamma is smaller than 1, so we can use subadditivity. Okay, this technical lemma that I presented just yesterday. So it's smaller than u1 to the gamma plus u k to the gamma. Okay, so that the lim sup when k goes to infinity of tau k to the gamma over k. Well, this is smaller than the limit of u1 plus uk gamma over k when k goes to infinity. Now, this thing u1, well, the sequence of ui to the gamma, it's an ergodic sequence, and it's an L1 ergodic sequence. So you can use the ergodic theorem. This thing converges to E0 of u1 to the gamma, which is just tau1 to the gamma, which is finite. Yes, which is finite because we have proved it. We have proved this implication. Okay, so this lim sup is finite, so this lim inf is positive. So, I mean, I don't know. This is we have only used very soft arguments, and we get a very non-trivial result. Okay, which is that. Well, we know that it has xn has 0 speed, but we know that it moves at least yeah, at this kind of a power velocity, okay? Well, not only we have used soft argument to get this result, but this result is, in a sense, sharp, in the sense that we've got the best exponent possible. Okay, so why? I think what this reasoning doesn't give you is an explanation of why this happens. Okay, why is this exponent driving the? And this is something we will see later when we start to understand. Okay, basically, why this product of rows appear in the expression of the quenched expectation of the mixing time. Okay, so. Now this is done. Any question about this? So we have another big piece in front of us, which is a computation of the quenched second moment of tau1. Okay. The idea was to prove this. If you remember, to prove this, basically we used Jensen with gamma. Now we want to use Jensen with gamma over 2, so we need the expression for the quenched expectation of tau1 to the power 2. Okay. So proposition E0 omega to 1 to the power 2. Okay, so this is equal to 2 times the sum from k equal 0 to infinity time. Okay, here you have rho 0 to rho minus k plus 1. Then you have the expectation starting from minus k of tau 1. And now the square is outside. Okay. So this is an expression we already know. And you don't have a bar. And then you have to subtract something. Okay, so this is what we are going to prove. So yes, perhaps what we can do first before proving this is to show that okay, I will be okay. Yeah, before proving this, perhaps we can show that this is enough to prove this thing for gamma between 1 and 2. Okay. So okay, so of 2 for gamma in 1, 2. Okay, so well, the assumption is that this is smaller than 1. We are trying to prove this. So what are we going to do? Well, this thing here, well, it's equal to the expectation of E0 omega to 1 to the gamma. And this is smaller, okay, just by Jensen. This is smaller than the expectation of E0 omega to 1 square to the gamma over 2. Okay. Now, we are going to use the inequality here, okay, without the negative term, because it's going to be easier. So we are just replacing this by this, okay, and we are using now the subadditivity lemma. So basically what we can do is put all these terms to the power gamma over 2. Okay, so it's smaller than, okay, I have 2 to the gamma over 2 in front, then I have the expectation, and then I have the sum from k equals 0. Okay, so let me subadditivity. K equals 0 to infinity, rho 0 to the gamma, rho gamma over 2, sorry, rho k minus 1, minus, I wrote k minus 1? No, it's minus k plus 1, yes. Gamma over 2. E minus k gamma. And this is tau minus k plus 1. Sorry. Omega tau minus k plus 1 to the gamma. Okay, so now I'm going to use translation invariance to say that this last thing, well, it's equal to 2 to the gamma over 2 times the sum from k equals 0. Okay, first thing, okay, the important thing here is that this term here, okay, we have its expression and we are going to use it, but in any case, this thing, it only depends on the environment that you see to the left of minus k. Okay? I mean, the environment that you see at minus k plus 1 doesn't count, because this is where you stop. And to the right, well, you see it even less. Okay, so therefore, it's independent of this. Okay, and these terms are independent. So, and also this thing, okay, just by translation invariance, you can add k here and here. It doesn't change the expectation. Okay, so what you get is this thing. E0 omega tau 1 to the gamma. Okay, and then you get the sum from k equals 0 to infinity. E rho 0 to the gamma over 2. Okay, so this thing here, it's finite. Okay, the assumption we have is about rho 0 to the power gamma, but if you remember the drawing I made last time, yes?
Shouldn't there be a power to the k or something?
Yes. Because if not, it wouldn't be finite.
Yeah.
So, yeah. So the important thing is that you have a geometric sum, and this thing is smaller than 1. Okay, just because basically, yeah, this thing means our assumptions means gamma smaller than gamma star. Okay. This gamma star, okay, might be infinite if you don't have this assumption that omega is smaller than 1/2 with positive probability, but it doesn't really matter. So if gamma is smaller than gamma star, then gamma over 2 is smaller than gamma star. Okay, so what we just have to care is the finiteness of this. And here, we are going to use our expression for tau 1, which is simply, okay, let me remember. Yeah, I don't have it written. That's a problem, but I think this was this, right? 1 plus 2 times the sum from k equal, well, 0 to infinity Okay. Yeah. Let's put k equal 1. Rho 0 rho minus k plus 1. I mean, okay, the expression is this one. You have 1 over omega 0 plus sum k equal 1 to infinity, 1 over omega minus k rho 1 rho minus k plus 1. And 1 over omega minus k, this is just 1 plus rho k. So yes, if you do this substitution, this is what you get. Okay, so in particular, this is smaller than this. Okay, it's not, just to simplify the writing. I just will have to write one big sum. Okay, so all good. So what can we say about this thing to the power gamma? Well, it's equal to this thing to the power 2 to the power gamma over 2. And now we are going to use subadditivity. Okay? We take this product, we expand it, and then we use subadditivity. Okay, we expand the square and then we use subadditivity. So what does this give us? Well, I guess the 2 is not very important, so you get 2 to the gamma in front. And then for the rest, you get the sum from j larger than 0, the sum from k larger than 0. And then you get rho 0, rho minus k plus 1, rho 0, rho minus j plus 1. Okay, so now if I don't care about a factor 2, I think I can only care, I can assume that j is larger than k, or k larger than j, whatever. And okay, then I have gamma over 2 everywhere, right? I forgot about it. Okay, and I get the sum. Okay, so let's say that k is the smallest. Okay, if you want, I put g prime. G prime is just j minus k. Okay, and here you get rho 0 to the gamma, rho 0 to the minus k plus 1 to the gamma, and then you get rho k to the gamma over 2, rho, what would it be? Yeah, minus k minus j plus 1 to the gamma over 2. Okay, so yes, so what we get is that E of E0 omega to 1 to the gamma. Well, this is smaller than a constant. Okay, this constant is just 2 to the gamma plus 1, so let's write it. Yeah, then you have the sum over k larger than 0, j prime. Okay, there is a prime here. J larger than 0, E rho 0 gamma to the k e rho 0 gamma to the j and gamma over 2. Okay, and this is finite. So, okay, what's the overall, okay, why does this computation work? It's basically because in the end, the leading contribution to this will be, okay, the leading contribution to, okay, to this, okay, it will be, okay, well, if you want to do it. Yeah, the leading contribution to this, okay, will be a product of rhos to the gamma, okay, and well, because this thing will be decreasing geometric sequence, you're good. Okay, and then this is reasonable to imagine that this is not specific to the exponent 2. This is already annoying to get when with 2, so yeah, I think if you want, you can try to do it for gamma equal 3, get the expression, and I think I will believe you if you give me the result. But okay, so basically, yeah, you can. This part you need a new ID. This part really you can prove it for any gamma finite if you find a way to systemize this. Okay. You don't need an equality here. You just need an upper bound which is good enough so that it works with this subadditivity argument. Okay. So any question about this? So now we can prove this. In theory, what you would have to do here would be to use a truncation argument first to prove that this thing is finite. But yeah, we are going to assume that it's finite and that everything converges. Okay, and I think this will be enough. Okay, so what we need to do here is basically to prove a recursion on this. So the recursion that we want to prove is the following. E omega tau 1 square is equal to 2 E tau 1 square minus 1 over omega 0 plus rho 0 E minus 1 omega tau 0 square. Okay, so why will this be enough? Well, if you have this, basically, you can iterate. So let me do one step. Okay, then you apply star to this term. So this gives you plus, well, 2 rho 0 E minus 1 omega tau 0 square. Okay, and Yeah, no, let me apply it. Okay, so what should I do? Okay, then, okay. So let me do it like this. Minus 1 over omega 0, minus 1 over omega minus 1 rho 0. Okay, so this is what comes from this term. Yeah, and plus rho 0, rho 1, e minus 2 omega tau minus 1 square. Okay, so yeah, what will happen next is that basically when you iterate, well, you will get the next term in this sequence, which will be 2 rho 0, rho 1, e minus 2 tau minus 1. And you will also get the next term in this sequence, which will be minus 1 over omega, minus 1 over omega 2, rho 0, rho 1. Okay, this sequence is just the expansion of this. So this is how you get things done. Okay, so let me write this. Just iterating. Okay. You get that e omega to 1 square. Well, it's equal to 2 times the sum from k equal 0 to n, rho 0, rho minus k plus 1, I guess, for rho 0, yeah. So when k equals 0, like, you have exactly 0 term in the product, okay, because it's the last index is the first index minus 1. It's really okay, then you have e minus k to minus k plus 1 square. Lots of indices. And then you have minus, okay, sum from k equals 0 to n, 1 over omega minus k, rho 0, rho, well, it's still minus k plus 1. And the last term, which is plus rho 0, rho n, e minus n minus 1 omega tau minus 1 tau minus n square. Okay, so this is just by iterating this thing, and then you let n tend to infinity, and you hope that this tends to 0. And of course, if you want to do things rigorously, basically, you put a truncation here, so this makes this thing automatically tend to 0. This gives you the desired upper bound, and now that you've proved finiteness, this gives you the lower bound. Because you can just ignore this last term. Okay. So now let's prove the star relation. Okay, so all these computations are not the most interesting things you can do, but I think it's also some sort of education, basically. In this field, there are lots of things that you can do without theory with just heavy computation. So this is part of what is done. Okay, and of course, it's not just heavy computation. You have to have some insight before starting the computation. But yes, I think it's well, it's a bit illustrative of things that have some time to be done. Okay, so let me do this. So, okay. E0 omega of tau 1 star. Well, I decompose according to the first step of the walk. So this will be omega 0 time. Okay, let me write this. Okay, plus 1 minus omega 0 times the expectation tau 1 square. X1 is equal to minus 1. Okay, so what's the... Okay, so this thing is equal to 1. Okay. Now this thing, okay, let's call it 1, let's call it 2. 2, it's equal to, okay, I'm using the strong Markov property, so I have E minus 1 omega, and now I have 1 plus, okay, so it's 1 plus tau 1, okay, just because I have to count the first step. Okay, but let me write this as tau 1 minus tau 0 plus tau 0, and let me put the square. Okay, and now what I want to do is I'm going to expand this square, so I'm going to get 6 terms. Okay, and so I have to figure out what these six terms are. So yeah, so what I observe is that under E minus 1 omega, tau 1 minus tau 0, and tau 0 are independent. Okay, this is just a strong Markov property. Once you reach 0, basically what you see afterwards is conditionally independent. Okay, so therefore when you expand, basically for all the cross terms, things will factorize. So what you get is that, okay, and this thing has distribution. Well, okay. E0 omega. Okay, this has the same distribution as this. This has the same distribution as tau 1 when you start from 0. Okay, so for this reason, this thing here, it's equal to 1 plus, okay, let me write all the non-diagonal term first. So plus E0 omega tau 1 square. Okay, so things are starting to appear. So this thing here, we are going to put it back on the left here. This thing here, we are going to keep it for the induction. And now we have 3 terms with a 2. We have E omega tau 1 plus E omega minus 1 tau 0 plus E0 to 1, E minus 1 to 0. Okay, so now, okay, we know what we want to do with these terms. Yeah, so perhaps can we already rearrange stuff? Yeah, let's try to do this. So, what we get? Okay, so. This I'm going to put it to the left. This one I'm going to keep. So what you get is E 0 omega to 1 square times omega 0, that comes from this term, okay, because you have, what am I right now? This is absolutely not that. You have this 1 minus omega 0 that gets subtracted here. Okay, so this gives you omega 0. This is 1 minus omega 0. Okay, because this term has a factor 1 minus omega 0 in front. Okay, this thing it's equal to, well, then you have 1, which is 1 times omega 0 plus 1 times 1 minus 1 omega 0. Then you have 1 minus omega 0 here. And then you have, okay, so this term has been accounted for, this term has been accounted for, we just have 4 terms left. Okay, so you have this one. And you have 2 times E0 omega to 1 plus E minus 1 omega to 0 plus the product of the two. Okay, so yeah, I know this is very annoying when you have to write things, but I'm going to do it again. So this becomes 1 over omega 0, and this is rho 0. So things are getting a bit more like what we want. So let's see. Okay, so this has the wrong sign. Okay, so we'll have to do something about it. This term is here is good. So yeah, what we have to show is that basically this thing here, it's equal to 2 rho 0 times omega 0. No. We have to get a minus. Okay, but perhaps we're missing another term. Okay, what's? No. Yeah. 2 rho 0. Yes, 2 rho 0. E0 omega to 1 square minus 1 over omega 0. Okay, if we prove this, we're good. Because this minus omega 0, it will cancel that one and bring a minus omega 0. Okay. No, it's 2 over rho 0. Okay, just to cancel this rho 0 here. You want rho 0 times this to be equal to that. Okay, so you will get the right term, and this minus 2 omega 1 over omega 0 will cancel this. Okay, so where is the simplification here? Well, we have the expression for this and for that. Okay, and I mean the expression, it's a product, and to obtain this one, you're just shifting things. So probably you can rewrite this one in terms of this one. Okay. So we are going to do this, replace, and this will end our proof. So what is okay, rho 0 times E0 omega, okay, E minus 1 to 0. Okay, this thing, it's, well, the sum from K equal 0 to infinity. Then you have, well, 1 over omega minus K. You have a minus 1 here that comes from the fact that you have shifted things compared to the normal expression. Then you have rho 1, rho, well, okay, if you want minus K, sorry, rho minus 1, and rho minus K plus 1. Okay, minus 1. Okay, so this is nothing more than the sum from K prime equals 0 to infinity of K prime equal 1 to infinity, sorry, of 1 over minus K prime rho 0 rho minus K prime plus 1. Okay, let me write plus 1 minus 1 here. Okay, I'm just taking the expression for tau 1 and putting minus 1 everywhere. Okay, this thing gives me the missing rho 0. Okay, so what I get is really this thing, which is just E0 omega tau 1 minus 1 over omega 0. Here I just have the first term missing. Okay, so what do I have? So now, if I look at the value of rho 0 times E0 omega tau 1 plus E minus 1 omega tau 0 factor of 1 plus E0 omega tau 1. I'm just ignoring the factor 2 here and putting this thing into factor. Okay. This is equal to rho 0 E0 omega tau 1 plus, now I'm replacing this, E0 omega tau 1 minus 1 over omega 0 1 plus E0 omega to 1. Okay. So now I think I have to group terms together, and this will be done. So, okay, let's see. Okay, first thing we get is E0 omega to 1 square. Okay, and then we have to take care about the rest. So then you have the term which is linear in the expectation. So you get rho 0 minus 1 over rho 0 plus 1. And this is equal to 0. It should be equal to 0. But it is equal to 0 because, yeah, rho 0 plus 1 is 1 over omega 0. Okay, and the last term you get is minus 1 over omega 0, which is what you wanted. Okay, it gets you the minus 2 over omega 0 that you want there. Okay, so yes, now the next step is oh yes, maybe I can write this thing here. So okay, we have proved an expression for this, okay, and therefore you get. I mean, okay, when we add power to the gamma, we used inequalities, but everything was were equalities when you were considering things to the power 2, right? So if you want the average the average of tau 1 to the square, I mean the mean of tau 1 to the square under the average law, you can compute it explicitly. And because we are interested in a central limit theorem, perhaps the right thing we want to compute is well, the variance of tau 1 under this. So let me give you the expression, and this is left as an exercise because it's just well, identifying geometric sequences. So exercise. The variance under E0 of tau 1, which is just E0 tau 1 square minus E0 tau 1 square. This is equal to 4, 1 plus E rho 0 E rho 0 plus E rho 0 square divided by 1 minus E rho 0 square 1 minus E rho 0 square. And this is if the expectation of rho 0 square is smaller than 1. Okay, so that this expression gives you indeed something which is positive. Okay, and this is what we call sigma 1 square. Okay, so this is one exercise and one first observation. The second observation is something that is going to be of interest for us to prove the quench central limit theorem. Is that if you look at the variance now under E0 omega of tau k, well, now because the increments of tau k, they are independent under the quench law, this is the sum of the variances. Okay, now just using the strong Markov property, you know that the distribution of this under this is just a distribution of tau j when you start from j minus 1. So ej minus 1 omega tau j minus 1. Now this thing is an ergodic sum. So this is the sum from I equal 1 to, well, perhaps I equal 1 to k, yes. Variance, and let me write it as this. E0 to 1. And now the important thing is I'm considering the shift on the environment. I mean, now the environment is acting by, yes, no, it's still shifting to the right. Okay, so this is, okay, so now I use the ergodic theorem, and we get that the limit when k goes to infinity of the variance of tau k divided by k is equal to sigma 1 square. Okay, which is kind of the first step you want to have if you want to prove central limit theorem. Okay, so let's take a short break, and then what we'll do in the remainder of the class is to talk about, well, central limit theorem when you have independence, but your variables are not IID. Okay, so yes. So if you use the ergodic theorem, you get that this converges to this. Okay. And this is slightly different. So, but no, is it different? Okay. No, it's okay. Yeah. Okay. So this is false. That's the point. The expectation. Yes. Okay, so this is the expectation of E0 to 1 square minus E0. Okay, take it with a grain of salt, okay? Make the computation. If you don't get exactly this, perhaps this was the other way around. But this is what I meant to write, okay? I wanted to give you an expression for this. Okay, and the other is strictly larger. Because it comes with another term, which is actually the variance of the expectation of tau 1, okay, when considered as a random variable. Okay, so yeah. So what about the ergodic theorem? So Linderberg central limit theorem for independent random variables. Okay, so here we have a sequence of random variables, but in general, it's better to consider what people call triangular arrays, meaning sequences of sequences. Okay, and well, sequences of finite sequences, because you at step n you only need a sequence of of size n. So okay, let x1 and xn n be random variable, okay, perhaps real valued random variables. Satisfying the following. So first thing, we want the variables to be independent. Okay, so here implicitly, what I'm saying is that we have a sequence of finite sequences. Okay, because we're going to be looking at things when n go to infinity.
You want the rows to be independent.
I want.
Yeah, the finite sequences should be independent. Is that it?
No. I don't really care about what happens for different n's. Yeah. And this is not I, this is j, because we are going to need I for something else in the proof. Okay, and this is not necessary, but this is helpful for notation. We are going to assume that they are centered, because if they are not, you're going to delete the mean. Okay, the second thing you want is that all xj n's are in L2. Okay, when I say centered, I already assume that they are in L1. Well, we say that E. Okay, let me put some simple E here for this theorem. E x j. And this thing, I will just call it sigma j n square. Okay. Yeah, I guess exceptionally, I won't put a square. Okay, it will be better for me when I write things. So this is not a property, this is a notation, so I put it there. Okay, and Sn square is the sum from j equal 1 to n of sigma jn. Okay, so Sn is going to be the standard deviation of the sum. Okay, so these two conditions, they are what the minimum you would require for a central limit theorem. There is a third one, because of course, if you have only 1 and 2, it's not difficult to find counterexamples to central limit theorem. The third condition is the following. You want that for all epsilon positive, the expectation of the sum from j equal 1 to n x j n square time the indicator that xj is larger than epsilon Sn. This thing, when n goes to infinity, it converges to 0. Okay, and the conclusion is, so limit when n goes to infinity of x1 n plus xn n divided by Sn is equal to n 0, 1. In distribution. Okay, or is equal to z, where z is distributed like 0, 1. Okay, this is a distribution, so if you put an equality, you'd better have variables on both sides. It's just good practice. Okay, so assumption 1 and 2 are very natural. The conclusion is very natural because it's a central limit theorem. So what about assumption 3? Well, this is called the Linderberg condition. Okay, you find it in this result, but also in many central limit theorems that are available for random variables with some kind of dependence. And what this thing guarantees, I mean, this is really the reason why it's necessary, is that like if you look at this as a process, okay, morally what it tells you is that in your rescale process, jumps of macroscopic size, they don't contribute to the variance. Okay, and well, because jumps of macroscopic size do not contribute to the variance, what you see is really a sum of small jumps. Okay, and this is the reason why you have the central limit theorem. So this condition, okay, it might seem a bit peculiar when you see it for the first time, but it's a very natural one. And as soon as it's not satisfied, you have kind of no hope to get something. Okay, I mean, unless the macroscopic jumps that you observe are by magic Gaussian, but I don't think this has much chance. Or if these things are so rare that you actually don't see them, and in that case, you might get a central limit theorem, but you will have a loss of variance in the limit. So the variance wouldn't be Sn, but, well, Sn minus this limit. Perhaps I should do something else here. Here you should divide by. Okay, it's a contribution to the rescale variance, of course. That is equal to 0. Okay, so first thing to do. Okay, we might be a bit short on time to prove the result. So let's prove the result first, and then we will see if we have time. I will tell you why this can be applied here. But okay, so how do we prove this? Well. Actually, you can either use characteristic functions, or you can use the substitution argument that we used last time. So let's do it with characteristic functions to vary a little bit. So proof. And the proof will rely on a lemma, which I will not prove, which is the following. Lemma. Let's assume that you have Z, J, N, J. Okay, so some kind of deterministic version of this theorem, if you want. So let's take a triangular array of complex numbers. Okay. Such that the limit when n goes to infinity of the sum of zjn from j equal to 1 to n is equal to z. And max of zjn when n go to over j, the limit when n goes to infinity is equal to 0, then the product from j equal 1 to n of 1 plus zjn, the limit of this is equal to exponential z. Okay, so I don't know if I've ever seen this lemma in calculus, but it's a standard calculus lemma. Okay, you just expand. Yeah, you just expand the complex log if you want. Formally, this is what you're doing. But what you can do is, expand, prove the convergence of the modulus and the argument separately. Okay. So, now we are going to use this to compute. Okay, what we want to compute is expectation exponential I psi over Sn times, let me call it S. Yeah, perhaps, I don't know, Zn. Is Zn good? Zn is x1 plus xn. Okay. So using independence, this is a product from j equal 1 to n of, let me write it in this way, 1 plus expectation of exponential I psi x j n over Sn. Minus 1. Okay, so we are left, okay, with proving a statement about this. Okay. Okay, I'm going to call this Z and J. Okay, and we want to prove some convergence statement about the Z and J's. Okay, so first, perhaps I should make a comment about about one implication of this assumption, which will somehow help us to prove this. Okay, so a consequence of star is that max over j of sigma jn divided by Sn tends to 0 when n goes to infinity. Okay, why is it the case? Okay. So what you have is that sigma jn, well, it's smaller than epsilon Sn, epsilon square Sn perhaps, plus the expectation of xjn Okay, epsilon SN square, index x, j, n larger than epsilon Sn. Okay, so the part of the variance which is contributed by small values, well, it's small. Okay, just by definition. Okay, and the other part, well, you know that it goes to 0 because even if you sum it over all j's, it goes to 0. Okay, so this ratio here, it's smaller than epsilon square for every epsilon. So, well, okay, the lim sup of this ratio. Okay, so this will help us to say that this thing has to be small. So yeah, let me rewrite Z and J. And Z and J, it's equal to, okay, so it's equal to, okay, I will put a first term, which is not very interesting. But it will help us. Okay, Jn. So this is equal to 0, but okay, so I will put just the two first terms in the Taylor expansion. And then I will put a third one, which I will call, okay, let me, okay, I will put a n, but, okay, and what is yjn? Well, yjn is just what you need to have for this thing to be true. So it's ei xi xjn over Sn minus 1 minus xi xjn over Sn plus xi square over 2Sn. X J N squared. Any typo so far? And there is something missing in the Taylor expansion? No, it's exactly, no. Sorry? In the? It's, there is a 2, yeah. Okay. Thank you. Okay, so this is, this is 0. This is sigma Jn. So we are kind of good, and here what you have is that, okay, yjn. So let's assume that. I don't think we need to do that, but yeah. So xi is a constant, okay, for as far as we are concerned. We are proving things for a fixed psi. So yeah, xi n. This just by Taylor expansion. This is smaller than what? This is smaller than a constant Okay, this is, I think this is smaller. Yeah, the derivative is 1 in modulus. So this should be, yeah, psi 3 over 6 y j n x j n to the 3. But okay, this is not really important. What I really need is just a constant time xjn to the 3. Okay, and now we don't have any information about the third moment. And we just have this information there. So this is what we are going to use. Yeah, so okay. This is really more a matter of reduction than anything else, but perhaps it will be more convenient to rewrite this condition in an equivalent fashion. So we are going to, okay, so from star, there exists epsilon n going to 0 such that the limit when n goes to infinity of Sn minus 2 expectation sum from j equal 1 to n xjn indicator xjn larger than epsilon Sn epsilon n Sn equals 0. Okay, is it clear for everybody how you get this sequence from this assumption? I mean, basically, you take epsilon equal to 1 over k, okay, and then you take you define a sequence nk in this manner, okay, which is yeah, in such a way that yeah, what you get over there is small. And okay, so yeah, we are going to use this in this fashion. So this is smaller. Okay, there is a constant that depends on epsilon. We just focus on this thing, and this thing is, well, the max between no, the mean. Sorry. Yes, I guess. Well, okay, xi 3 over 6, and then I get xjn to the 3. Okay, and epsilon n xjn. Okay, we are just considering now as a, basically, when this is smaller than epsilon Sn, we are going to consider the cube. When this is larger, we are going to consider this as a bound. Okay. So I guess so So what we have is that really zjn, it's equal to what? To minus sigma jn over Sn square. This thing will exactly sum to minus 1/2 xi square. Sorry. So this thing here will exactly sum to minus xi square over 2. So using our lemma, we will be good. Plus, well, if you want, rjn. And yeah, so not only it will sum, but also it will satisfy the assumption. Then we have something else, and we just need to show that this sum of rjn converges to 0. Okay. Okay, and yeah. I mean, if you have this with absolute value, you're sure that your rjn's do not mess up with your condition on the max. Okay, so yeah, so now what you have is that rjn, well, it is smaller than a constant times the expectation of x j n to the 3 epsilon n s n x j n to the 2. Okay, so I'm thinking, okay, we are probably missing something here. Yes, okay, I'm sorry. Well, this bound is true, but it's not really useful. Basically, when this is big, this bound is bad. Okay, so you want to get something better than that, and basically, so I won't tell you what the constant is, but you can get that this is smaller. Okay, let's assume that psi is not 0, but I'm not sure it changes anything. But yeah, and here you have max of psi x j n over Sn cube and x j n over Sn squared. And here you have the mean. Okay? Basically, what we mean there is that when xj over Sn is smaller than 1, then this is a good bound, because this is a good bound all the time. And when xj over Sn is larger than 1, this is a good bound. Okay, for the exponential, 1 is a good bound. So the largest term we had here in our the largest term we have here is this one. Okay, and this is one. Okay, so if you're interested in computing the constant c, you can, but it's not necessary and it's not very interesting. Okay, so now we can proceed. So yes, you get the mean, okay, between xjn over Sn cube and xjn over Sn square. Okay, and yes, so now when now we are going to do something slightly suboptimal, but that will be sufficient for what we want to do. when xjn over Sn is smaller than, well, when this quotient is smaller than epsilon n, we are going to use this bound. Okay, so xj over Sn to the 3, index xj over Sn smaller than epsilon n. And well, in the other cases, we use the other bound, so xj over Sn square, index xj over Sn larger than epsilon a. Okay, so now what we have is that the sum of this goes to 0 when n goes to infinity because of star. Okay, this is exactly our condition. This is exactly the sum that appears in the theorem. And now what about the first term here? Okay, and here I have absolute values. This is important because about this. And yes, so now this thing here, it is smaller than, well, epsilon n times the expectation of xj square over Sn square, okay, which is equal to sigma jn over Sn square times epsilon n. Okay, so if you sum everything, you get epsilon n. This tends to 0, so you're good. Okay, so it's technical, but the proof is quite natural. You could do, I mean, also with this thing of substitution. Basically, after using Taylor expansion up to order 3, well, you do something with your rest. Basically, you want to say, to control my rest, what I can do is, well, if the variables I have are small, I can use second moment. I can say, okay, what I have does not contribute to the variance, so the sum of the third moments it will be. And if they are large, you're using this condition, and all is good. Yes, so this concludes the proof of this. Yeah, can I explain in one sentence how you use the, yeah, so let's say in one sentence how you use this theorem to prove what we want. So the application, you want xjn, well, it's equal to tau j minus 1. Okay, so well, Sn, in that case, Sn square is the variance of tau k. So we already know that this is equivalent to n times sigma 1 square. Okay, so this is going to be good. I mean, if the conclusion holds, things are going to be to go right, because here what we would get is that tau n over square root of n tau n over Sn square converges to z in distribution. And yeah, so if you take tau n over square root of n, well, this is equal to tau n over Sn times Sn over square root of n. And this thing here, it converges almost surely to sigma 1. Okay, so what is really important here is to check that the Linderberg condition is satisfied here. And how do we check the Linderberg condition? Well, using what we do all the time now, we use the ergodic theorem again. So, okay. Yes, so what can we say about this sum here? Well, this sum here, okay, I will write it, okay. So I will write a version of it, which is not very different. So I will replace Sn squared by k, because these two things are equivalent. Okay, and I would like to look at, well, E0 omega sum from well, I equal 1 to k. Okay, UI. Okay, UI is just tau I minus 1. And then I take the indicator, the UI square indicator that UI is smaller than epsilon square root of k. Well, again, this is not exactly the standard deviation, but it doesn't change anything because asymptotically they are comparable. Okay, and I would like to prove that this goes to 0. Well, what I can say is that this is smaller than, basically, what I don't really like here is that I have a dependence in k. But apart from that, this would be an ergodic sequence. So I can upper bound this by this. And yeah, so sorry. Okay, so this is true for k sufficiently large. Okay, and this thing okay, if you take the limit of this, so now you have a bound on the lim sup. Well, here you have an ergodic sequence, so the limit of this is nothing more than E0 U1 square, indicator that U1 is larger than M. Okay, and this is true for every M. And taking M large, this goes to 0. So you get the Linderberg condition. Okay, so yeah, this concludes the proof of the quench central limit theorem. Now for the average central limit theorem, I realize that really, if you want to use the ergodic central limit theorem that I mentioned, it really comes, okay, at least every proof I've seen of it so far, it comes on top of a construction which is quite long, okay, because you first need to prove martingale central limit theorems. So yeah, either we will skip a part of this proof, or we will do it by hand. Okay, I will have to decide until Friday what we do about this. Okay, but well, either you will have to accept some part of the result, or we will do a computation by hand, and then we will prove the average central limit theorem for the tau case, and try then to convert it for xn, at least in one case. Any question? Okay, so see you on Friday.